We want to make sure this quiz sense to it. So identify the strongest nucleophile in a Sn2 reaction. Kind of wish it said which would be the most nucleophilic in an Sn2 reaction, but I think you'd want the same answer, the ethoxide ion. Consider the substitution reaction that takes place when R3-bromo and 3-methylhexene is treated with sodium methoxide. So what do you want to figure out? We have a tertiary alkyl halide. What do you know about tertiary alkyl halide? Tertiary alkyl halide. So this has been up on the Moodle page. Let me draw your attention to it. Sodium methoxide. Is the base strong? Yes. Sn2 and Sn2 and E2 can occur. Is the nuke a strong base? Yes. Alright. Is the alkyl halide tertiary? Yes. That means E2 occurred. So you got to come all the way down here and select an E2 reaction would take place during which the stereogenic center is locked. And if we had to draw the product, we would draw this thing here. Any questions on that first? What is the major product that results when 2R3S2-chloryl-3-phenyl butane is treated with sodium methoxide in methanol? So when I did this, I said, oh, secondary alkyl halide, that can undergo substitution. And I did the substitution reaction, got my product, and then I said to myself, I don't see that answer. So I drew this thing out, and then I said substitution would get inversion of the stereo center, and then I named this. It wasn't on the list. This is wrong. This would be S. Made the molecule look something like this. This is how I have it drawn. Well, you can't see that with my dark shirt on. Alright. So I have something that looks like this on my paper. Highest priority second. That's clearly R. Inversion. Imagine this is now the methoxy group. That's clearly S. So I didn't have a model kit when I was working through this to make the key. So I did it in my mind's eye by drawing this picture. So let's just go to this thing here. Is the nuke strong? Yes. Is the nuke a strong base? Is the alkyl halide tertiary? No. Is the alkyl halide primary? No. Is the alkyl halide secondary? Should be a yes here. So it says I can get both Sn2 and E2. And if it's heated, I'm going to get a little more E2 over S1 perhaps. Main point is we get a mixture. So the next thing to figure out is I said to myself, I need to get the alkyl halide and the halide and the carbon antiplanar to each other. And here was my first attempt, and I said, I'm going to start over. So I'm going to go back to my model kit, and I got it antiplanar. So there's the hydrogen, there's this, and then I can say when base comes and grabs that hydrogen, those electrons jump down and chloride leaves. I'm going to get this thing here. And that might be a bit hard to see. So here's the R. So my picture, I have it drawn like this. I get the halide and the hydrogen antiplanar to each other. And then if I look at that, I'm going to replace this with a double bond. Imagine this being flattened out. And then I can see the E configuration. I could put a double bond there, and I'd have the E configuration. All right, so once I figured out that the Sn2 was not an option because it was wrong, that's why you want to know your stereochemistry. So then this is the outcome here, and this is the E2-phenyl-2-butane. Any questions on that one? No? That one should have been a two-pointer maybe. Predict the most likely mechanism when 2-iodohexane is heated in ethanol. 2-iodohexane. Is the nuke base strong? No. All right, so we have our first order kinetics. Is the halide tertiary? No, 2-iodohexane. That's going to be secondary. All right, is the alkyl halide primary? No, so that defaults to secondary. Sn1 and E2 can occur. So either way, we're going to get Sn1 and E1 products. And everybody, I think everybody knows this. All right, draw the major organic product that is generated in the reaction below. Pay particular attention to regio and stereochemical details. All right, here's our alkane. This is the boreation or hydroboreation. And what we know about this, it's anti-Makarnikov and it's Sn addition. And it's virtually hydration of a double bond. Hydration of a double bond gives us an alcohol. Makarnikov puts the OH here. This is anti-Makarnikov, so we want to put the OH there. And the OH and new hydrogen add to the same face of the ring. So you had to denote stereochemistry to get full credit on that one. And you can see the poor carbon got richer. The carbon that already had a hydrogen still has it. I didn't draw it in. You can imagine it's there. Any questions on 5? Moving right along, draw the structure of the major organic product for the reaction below. So this is the halohydrin formation. The intermediate looks something like that. And then the water comes and hits, and it's going to hit on the more substituted carbon. So that means in the end, bromine's going to be on this carbon, the OH. Bromine's going to be on this carbon. The OH is going to be on that carbon. And here we go. So why do I have my wedge here and my dashed wedge there? This is a anti-addition. And this down here is an anti-addition. Anti is opposite faces, opposite sides of the ring. Draw the major organic product generated in the reaction below. So if we tried to do this without using the mercury demercuration reaction, we'd get a carbocation rearrangement, and I'd have the OH here, because this hydrogen here would migrate up to where the carbocation gets formed. And so there is where the OH goes. This is also an anti-addition thing, but since we don't have a ring, we get a sigma bond that spins. Any questions on that one? Moving right along. When trans 1-iodo-4-methyl cyclohexane is heated in methanol, the product mixture is primarily, let's just go through this for fun. Is the nuke base weak or strong? It's weak. Is the alkyl halide tertiary? No. Is it primary? It's secondary. So Sn1, E1. Look through here. There's no E1 products listed. This would only be with Sn2. Get rid of that. So what we might want to do is figure out the reaction mechanism. Now, it said this thing was trans. There's my carbocation intermediate. So when methanol attacks, it can either come from the top side of the ring and give you this product, or it can come from the bottom side of the ring and give you this product. So these two products, they are not mirror images. They have the same order of connectivity. So we know they're not enantiomers, but they are distereomers. So we get a mixture of distereometric ethers. Any questions on that one? When 1-bromo-2,2-dimethyl cyclopentane is heated in ethanol, one of the products which results as shown below. Provide a detailed stepwise mechanism for the production of this compound and give the name of the mechanism. So once again, since we have a weak nucleophile, we're going to come over here and see that the E1 and S1 are options. And of course, we're looking at the alkene. So we know right away it's an E1. All right, so that gives the name of the mechanism. So how does that mechanism work? Bromide leaves. Here's this secondary carbocation. Then we have a methyl shift. Now over there I have a tertiary carbocation. Here's ethanol, acts as a base, grabs this proton. These electrons move down. and we get to our product. Formation of the carbocation is the rate limiting step. Any question on all those? Extra credit questions? What is the major organic product of the following reaction? Alright, so we have a tertiary alkyl halide. This thing is strong, but bulky. So it's a bulky base. What that means is the bulky base can't get in there to grab that proton. That would give you Zeta's product. Since we have the bulky base, we get the Hoffman's product. Any questions on that one? When 1-bromo-1-methyl is heated in methanol, 2 alkanes and an ether are formed. Draw a detailed mechanism for each product form and circle the major product. So we have a tertiary, and the methanol, that's a weak nucleophile. So it's going to be unimolecular kinetics. Bromide leaves. Here's a carbocation. Methanol comes along, pulls that off. And when we pull it off here, we get Zeta's product. If we pull this one off, we'd get this product. We're going to get a whole lot more of this thing because of Zeta's rule. And then if this acts as a nucleophile, hits there, got oxygen protonated, this comes off. So here's our ether, and here's our 2 alkenes. The major product, let's just go through this thing for fun. Is the nuke base strong? No, it's weak. So Sn1, E1 can occur. Is the alkyl halide tertiary? Yes. E1 and Sn1 go to heat. That means come all the way down here. Heat favors E1 over Sn1. So that's why we're going to want to circle this one here. Here's our 3 products, 2 alkenes and an ether. Any questions? Yeah, buds?